class. This is Econ 510 Managerial Economics class. Today is February 3rd, Thursday. The class will cover Chapter 4 of your textbook. So today we cover the first half of Chapter 4, and the next Tuesday we will cover the second half of Chapter 4. Topics of today's class include understanding utility theory, 2. Finding consumer equilibrium, 3. Constructing consumer's budget constraint, 4. Understanding a change in budget constraint, 5. Understanding indifference curve. So let's watch individual video clip.
Utility theory is the tool economists use to describe the way households allocate their limited budget across the array of goods and services that provide satisfaction. Why is it that most consumption bundles are balanced? They contain some apples, some oranges, some milk, some eggs. Why don't consumers spend all of their income on one particular good or service that's especially satisfying and buy very little of anything else? Utility theory can help explain the balance in people's consumption bundles. Utility theory has at its root a unit of measure called the util, and a util is an increment of satisfaction. For instance, if I have a potato chip, and I do like them, I might measure my satisfaction by creating this fictional measure of happiness called the util, and the first potato chip that I eat adds 10 utils to my satisfaction. Think of this as a kind of psychic payoff from the pleasure of eating a chip. The marginal utility of consuming a potato chip is the additional utility, the extra number of utils that are added to my total satisfaction when I consume that first potato chip. So its marginal utility, or psychic satisfaction, is equal to 10. That means if I eat one potato chip, my total utility is 10 utils. So good. Now, suppose I decide to have a second potato chip. I'm sorry, so good, but not quite as good as the first one. I mean, after all, marginal utility does diminish. The second potato chip is never quite as good as the first one, even though it's still quite delightful. The total utility that I get from eating 2 potato chips is 10 for the first plus 8 for the second, for a total utility of 18. Of course, no one can eat just 2, right? The third chip adds only 6 utils to my total satisfaction, bringing the complete level up to 24. I mean, it's better than nothing, but not quite as good as the first 3. My total utility, however, is still increasing for a while. I mean, it was there, right? So I ate it, but I can't say it was especially enjoyable. Okay. Can I have a glass of water? mean, is the point clear? More is better up to a point, but each additional unit provides a little less satisfaction than the unit before after some point. Consumption is subject to diminishing marginal utility. Each additional unit that you consume in a set period of time, other things held constant, is going to provide less satisfaction than the unit before. This means that while more of everything may be better, eating more potato chips at any given point of time, after some point, becomes a bit of a chore. Marginal utility can fall to zero and even become negative. So now we'll show how to apply this tool as we calculate the way consumers choose to spread their income out over its competing uses. But first, I'm going to take a break. We're ready to tackle the problem of consumer choice. That is, how will a household allocate its scarce income across the goods and services that provide it with satisfaction? For instance, how much of our snack budget will we spend on apples and how much will we spend on candy bars? The answer to this problem hinges on utility theory, and it turns out that the rule the household uses to allocate its income across competing uses is this one. The household will continue to shift its money between spending on apples and spending on candy bars until the marginal utility per extra dollar spent is equal across the two goods. Let me give a simple example to show how this principle works. Suppose we're going shopping and we have a limited budget, say $6, to spend on apples and candy. How much will we spend on each? How many candy bars will we buy and how many apples? Suppose we start putting candy bars into our shopping basket. It costs $1 to buy a candy bar, and the first candy bar that we put into our shopping basket gives us a psychic satisfaction of 10 utils. So right now we're getting 10 utils per dollar from our purchase of chocolate. Suppose we also put an apple into our shopping basket, and the first apple that goes in provides us with psychic satisfaction of 8 utils. Now, since apples only cost 50 cents, these 8 utils average out to 16 utils per dollar. That is, at the moment, we're getting more marginal utility per dollar spent on apples than we are on chocolate. So let's go ahead and put another apple into our shopping basket since they're such a good deal at providing us with satisfaction. The second apple also costs 50 cents, and it provides us with a little bit less psychic satisfaction than before, only 6 utils. Well, 6 utils for 50 cents comes out to 12 utils per dollar, which is still more than we're getting from chocolate. So we'll go ahead and buy another apple. This third apple provides us with an extra utility of only 3 utils. So 3 utils for 50 cents amounts to 6 utils per dollar. Now chocolate looks like a better deal. So let's go ahead and buy another candy bar. For $1 spent, this next candy bar provides us with psychic satisfaction of 8 utils. 8 utils per dollar is better than 6 utils per dollar, so chocolate still looks like the best buy. Keep spending on chocolate. Here we spend another $1, and the third chocolate bar provides us with a marginal utility of 5. So now we're getting 5 utils per dollar from chocolate. 6 utils per dollar from apples. That means apples are looking good again. Let's put another apple into our basket. And this apple is going to give us a psychic satisfaction of 1 util. 1 util for 50 cents spent is 2 utils per dollar. So now chocolate is now the preferred way of spending our snack money once again. Spend another $1 on a candy bar, and that gives us a psychic satisfaction of 2 utils. 2 utils per dollar on chocolate is equal to 1 over 50 cents, or 2 utils per dollar on apples. So now at the margin, an extra $1 spent on either snack is providing us with the same amount of satisfaction. Over here we'd get 2 utils from spending $1 on apples, and over here we'd get 2 utils from spending $1 on chocolate. Good thing that we've equilibrated the two, because now we're out of money. That is, the consumer is going to keep shifting money between the two until marginal utility divided by price is equal for the two goods. There's no reason for us to do without an apple so we can have more chocolate, because then apples would be providing more satisfaction than chocolate at the margin. We'd want to go right back to what we were doing before. And there's no reason for us to do without a candy bar to have an extra apple, because the candy bar we'd be giving up is providing us with more satisfaction per dollar spent than an extra apple would. And if we add up the money spent, 50 cents, 50 cents, 50 cents, and 50 cents, plus $1, $1, $1, $1, we've now spent our entire snack budget of $6, and we've allocated it across apples and across chocolate in such a way that the marginal utility for an extra apple divided by the price is equal to the marginal utility of an extra chocolate bar divided by the price. We spent our limited income, and we spent it across two goods in such a way that an extra dollar spent provides us with the same extra satisfaction, whether we're buying apples or chocolate. This is the rule that households use to maximize satisfaction from a limited amount of income. You are in the coolest store in the world with all of your favorite stuff. I mean, we have got the ping pong ball pistol, and, you know, we've got cupcakes. What are these called?
Buttercream.
Buttercreams. We've got moon pies. We even have a crocodile whistle. What are you going to do? You say, I want it all. Well, of course you do. You're an insatiable consumer. But there's a problem. The problem is you've only got so much money to spend, and this stuff ain't free. You're going to have to pay $3 to get the punching monkey. You're going to have to pay $1 for a package of circus peanuts. How are you going to spend your limited budget when you have to choose between Krispy Kremes and Squeaky Nuns? Well, it's tough. So we're going to help you by introducing some economic tools that we use to describe consumer choice. The first set of tools describe what's possible or feasible. These are the tools that describe the amount of money you've got to spend and the combinations of toys and snacks that you can afford on your limited budget. That is, we're going to start with what we call the budget constraints. Then we're going to move to a representation of your preferences. That is, how you would make trade-offs between Bunny Bowl and snacks. That is, we will come up with a set of indifference curves that represent your preferences for toys and snacks. Then we'll put the curves together with the constraints. We'll put what you want together with what you can get and come up with a prediction of how you'll shop. That is, we're going to derive a demand curve and show how you respond when you're given a set of constraints and a set of opportunities. And we'll use that to connect it with a tool, the demand curve, that you're already familiar with. So let's get started. The first thing we're going to do is clear away these infinite possibilities and focus on what's feasible for you, given the constraint of your income and the price of the products that you want to buy. So let me do that. Make a little space here to do a little rigorous math work. And the first thing we're going to do is derive a budget constraint. So let me put some axes here in my picture. Whenever you're doing consumer choice, you're going to be drawing graphs that we describe as goods space. Goods space means you're measuring quantities of goods on each of the two axes. So on the vertical axis, we're going to measure snacks. And on the horizontal axis, we're going to measure toys. And this is how you make your trade-off between toys and snacks, is you choose a point in this space. For example, this point here might represent 2 toys and 2 snacks, and this point here might represent 12 toys and 4 snacks. Sorry, I'm wrong, aren't I? 12 snacks and 4 toys. So you've got to be careful. The horizontal coordinate tells you how many toys you've got, and the vertical coordinate tells you how many snacks you've got. Now that we've got this picture of goods space, we're going to use it to represent your budget constraint. That is, what are all of the combinations of snacks and toys that you can afford to purchase given your limited income? Well, if you want to put together a budget constraint, you're going to need some information. The first piece of information you need is how much money do you have to spend in this store. Let's suppose you have $12 to spend. $12 to spend on whatever combination of snacks and toys you choose to purchase. The second piece of information that you're going to need is the price of a toy. And let's say that toys are selling for $3 a piece. So the price of a toy is $3. Let's say that the price of a snack is $1. That's the third piece of information you need. How much does a snack cost? Well, now that you've got these three pieces of information, your total income or budget, your price of a snack, and your price of a toy, you can describe all of those combinations of toys and snacks that you can afford to purchase. I like to start by finding the endpoints on my budget constraint. Suppose you spend all of your income on snacks. How many snacks will you be able to buy? Well, you have $12 worth of income, and snacks cost $1 a piece, and that's going to give us a total snack purchasing power of 12 snacks. If you converted all of your income into snacks, you could buy 12 snacks. Now let's suppose instead you bought only toys. How many toys could you afford? Well, with a budget of $12 and a price per toy of $3, then you can afford to buy 12 divided by 3 equals 4 toys. So the endpoints are 12 snacks and 4 toys. Now, what about combinations that have some of each in them? Let's suppose you decided you wanted to buy 2 toys. How many snacks could you afford to buy? Well, 2 toys will cost you 2 times $3 equals $6. Subtract 6 from 12, that leaves you $6 to spend on snacks. And since snacks are $1 a piece, you can afford to buy 6 of them. So 1 point on your budget constraint will be 2 toys and 2 for 6 snacks for a point like this. Let's calculate another point on the budget constraint. Suppose now you only buy 1 toy. How many snacks can you afford to buy? You calculate it. One toy costs $3. Subtract $3 from your budget of $12, that leaves $9 to spend on snacks. And since snacks cost $1 each, you can afford to buy 9 snacks. Another point on the budget constraint. One more point. Suppose you buy 3 toys. How many snacks can you afford to purchase? With 3 toys, you can afford to buy 3 snacks. 3 toys cost you 3 times $3 is $9, subtracted from 12 leaves you $3 for snacks, and since snacks are $1 a piece, you can afford then 3 snacks. If we kept doing this, we would be generating more and more combinations of toys and snacks that you can afford, given their prices and given your $12 worth of income. Eventually, when we connect these dots, we will get the budget constraint. The budget constraint will be the point. The budget constraint is the collection of points that shows all the combinations of toys and snacks that the consumer can afford to purchase given their fixed income and the prices of the goods. That is, all of these points along this line represent feasible combinations of toys and snacks, combinations of toys and snacks that you can afford. The way to represent this line is to manipulate the budget constraint. Let's write the budget constraint down and then let's change it algebraically. The budget constraint says that the income that you have to spend, M, will be equal to the price of toys multiplied by the number of toys that you buy, plus the price of snacks multiplied by the number of snacks that you buy. Well, since snacks are on the vertical axis, we want to isolate our snack variable in terms of all the other variables. The first thing that we'll do is we'll move toys to the other side of the equation. M minus the spending that you do on toys is equal to the amount of money that's left to spend on snacks. Now, divide both sides of this equation by the price of snacks. And I'm also going to move snacks to the other side of the equal sign. And I get this. The total number of snacks that I can afford to buy is equal to my income divided by the price of snacks minus the price of toys divided by the price of snacks multiplied by the number of toys that I buy. This equation that I've drawn is the equation that I've graphed here in goods space. This is the equation for this line, which is the budget constraint. The way to understand this equation is this. The total number of snacks that you're able to afford is equal to what you would be able to afford if you spent your entire income on snacks. That is 12 divided by the price of snacks of $1 for a total of 12 snacks, minus the number of toys that you buy multiplied by the relative price of toys and snacks. That is, since toys are $3 a piece and snacks are only $1 a piece, each toy that you purchase is going to cost you 3 snacks. You have to give up 3 snacks to get each toy. The negative sign lets you know that the line is downward sloping. But this relative price term, the price of toys divided by the price of snacks, is important because it's the opportunity cost of getting another toy. The opportunity cost of buying another toy is this number right here, or the 3 snacks that you have to give up to get that toy. We're considering how to represent your choices in the world's coolest store. You have a limited amount of money to spend on toys and snacks, and you want to spend it so as to get the most satisfaction. Last time, we looked at this equation. This is the equation for the budget constraint. It tells you how many snacks you can afford to buy given your income, the price of snacks, the price of toys, and the number of toys that you choose. When we graphed this, we got the vertical intercept, which is the purchasing power of your income measured in snacks. That is, the total number of snacks you can afford to buy, given your income and prices. And we got the horizontal intercept, which is the total number of toys you can afford to buy. The slope of the budget constraint, which is this number right here, tells you the opportunity cost of an extra toy, measured in terms of the number of snacks you have to give up. What I want to do now is show you how this constraint changes when we change some of the things in the economic environment. In particular, what happens to your opportunities when your income changes or when the price of the products changes. Let's start with your income. What happens to your feasible set? What happens to your budget constraint, or the stuff you can buy, when your income is reduced? Let's suppose instead of having $12 worth of income, you only have $6 worth of income. In that case, how many snacks could you afford to buy? That's right, 6. And how many toys could you afford to buy? 6 divided by $3 per toy is only 2 toys. Now, the relative prices of toys and snacks are still the same. We haven't changed them, only your income. The way we show a change in income in this picture is the budget constraint will shift. In this case, it shifts inward because your purchasing power has shrunk. You now have a smaller set of toys and snacks that you can afford because of a reduction in your purchasing power. If your income should increase, the feasible set shifts outwards. That is, you can afford to buy more toys and more snacks. These intercept points, again, represent your purchasing power, what you can afford to buy, how well off you are measured in terms of toys or snacks. The slope of the line, however, again, still refers to the opportunity cost of toys measured in terms of snacks. Let's look at a second possibility. Suppose now, instead of changing your income, we change the price of toys. And let's cut the price of toys in half. Now, instead of costing $3 to buy the punching monkey, you can get the same punching monkey for only $1.50. And let's suppose the same is true for the vibrating sea mine and the squeaking nun. If all of our toys are now $1.50, how many toys can you buy with a budget of $12? The answer is you can afford to buy 8 toys. 8 times $1.50 equals your $12 income. Now, your purchasing power in terms of snacks has not changed. Snacks still cost $1 each, and you only have $12 to spend. So we show a change in the price of toys by rotating the budget constraint like this until we reach its new intercept. This is the budget constraint when toys cost $1.50 a piece, snacks cost $1 a piece, and you still have $12 to spend. A movement in the budget constraint, therefore, represents a change in your opportunities, a change in what you can buy, given your income and the price of the goods. If your income changes, then the budget constraint shifts outward for an increase in income and inward for a decrease in income. But the slope remains the same. As long as prices don't change, the slope remains the same. If we change the price, on the other hand, of one of the products, say toys, then we have to pivot the budget constraint. The budget constraint moves outwards in the direction of the product that's become less expensive. Now, instead of only being able to afford 4 toys on your $12 income, you can afford 8 toys, and that's why the horizontal intercept has moved out. Notice, because toys are less expensive now, you can afford to buy more stuff than before. The budget constraint has pivoted outwards. In the future, then, when you change the income, shift the budget constraint parallel. Keep the slope the same. But if you change the price of one of the goods, make sure that whichever good is becoming less expensive, that you're shifting the budget constraint outwards in that direction, in the same way that you would be shifting it inwards if one of the products became more expensive. This is how you manipulate the budget constraint to describe a change in the consumer's opportunities, a change in the feasible set of things they can afford. Think fast. Which would you rather have? 4 toys and 3 snacks, or 6 toys and 2 snacks? Would you be willing to give up your animal crackers if it means that you could enjoy the dinosaur pistol and the bunny bowl? Which would you rather have? 4 and 3, or 6 and 2? Maybe this is hard to figure out real quickly. Maybe it isn't. Maybe you'd just as soon have one as the other. We're now going to explore a tool that economists use to represent consumer preferences. This tool is called the Indifference Curve, and it becomes part of a map that represents all the combinations of goods that you find more, less, or equally desirable. Once we've drawn a map of indifference curves, we can put the indifference curves together with the budget constraint and derive the consumer's demand curve. That is, once we know what your constraints are and what your preferences are, we can use them together to predict your behavior. So let's get right to it. How do we draw an indifference curve? An indifference curve is defined as a set of points representing combinations of 2 goods, like toys and snacks, that a consumer finds equally desirable or equally satisfying. So we have to begin with a list that the consumer provides us that tells us those combinations that he or she finds equally desirable. Suppose we have a consumer named Chris, and we quiz Chris about toys and snacks, and he provides us with this list. This list tells us that Chris would just as soon have 2 toys and 6 snacks as 12 toys and 1 snack, or 4 toys and 3 snacks, or 6 toys and 2. All of the combinations represented on this table provide Chris with an equal amount of satisfaction. That is, Chris is indifferent among each of these alternatives. He'd just as soon have this one as this one or this one. Let's represent now Chris's preferences in a graph. Here we are back in goods space, and let's remember to label our axes. That's always important. The vertical axis is going to represent the number of snacks that Chris has, and the horizontal axis, just like before, is going to represent the number of toys that Chris has. Now let's take the information from the table and represent it in the picture. So we'll start with the combination of 2 toys and 6 snacks, and that will represent with this red dot right here. Next, we find the combination of 4 toys and 3 snacks equally satisfying, so we can put that point right here. Then 6 toys and 2 snacks gives us this point, and finally 12 toys and 1 snack gives us this point. All of these points represent combinations of snacks and toys. And all of these points, according to Chris's report, provide him with an equal amount of satisfaction. Now, you can imagine that there are a lot of other combinations in between these dots that represent combinations of toys and snacks that Chris finds just as satisfying. We can represent these infinite possibilities by connecting the dots and drawing a curved line that we call an indifference curve. So here I go, connecting the dots. And there's my indifference curve, a collection of points representing combinations of snacks and toys, all of which Chris finds equally satisfying. Looking at this indifference curve, you'll notice I drew it pretty carefully. I'm trying to make sure that the way I draw the indifference curve is consistent with what economists believe about people's preferences. Let me be specific. The first thing you'll notice about this indifference curve is that it's downward sloping. The downward sloping indifference curve means that both of these goods are desirable. That is, if we take away some of Chris's snacks, the only way that we can leave him just as happy as he was before is to give him some extra toys. Anytime we take away one of the goods, we have to compensate by increasing the quantity of the other. And that gives us a downward sloping indifference curve. Every time we lower snacks, we have to increase toys. It's another way of saying that more is better. If we had a combination of toys and snacks that represented an increase in both, well, Chris would prefer that, so it would have to be on another indifference curve with another set of combinations. For instance, suppose we consider a point like 2 for 6 snacks and 2 for 6 toys. Since that represents more toys and more snacks together than any of these points in here, that would be a point that would be way out here on another indifference curve somewhere. So a point that has more of both goods than a point on this curve would be more satisfying, and therefore it would lie on another curve somewhere, a curve that represents increased satisfaction. Another thing to notice is I've drawn this curve sagging downwards. We would call this a convex curve because it's bowed downwards towards the origin. A convex curve is a curve that has a decreasing slope as you move down it. Notice up here the slope is very steep. Then the slope gets a little flatter, and finally down here towards the bottom, the slope of the curve is very flat. Now you'll recall from our early math review that the way you find the slope of a curved line is to take the slope of a line that's tangent to the curve. So for instance, if we want to know the slope of this indifference curve at this particular point with 4 toys and 3 snacks, we would look for the straight line that is tangent to or touches the curve at that point. And that tangent line's slope is the slope of the indifference curve at that particular point. Notice that the slope of the tangent line as we move down the indifference curve is getting flatter. The slope is decreasing. The line is getting flatter as we move down the curve. Well, that's just a mathematical statement about what convexity means. But actually, this convexity has an economic interpretation. Notice that when you're way, way up here, whenever Chris has a lot of snacks and very few toys, the curve is steep. That means if we take away a lot of Chris's snacks, we only have to give him a few toys to compensate. Or to put it another way, if we take away one of his precious toys way up here, we have to get him a whole lot of snacks to leave him as happy as he was before. Just one toy less means a whole lot more snacks to leave him at the same level of satisfaction. Whereas if you're down at a point like this, and you take away one of his toys, you hardly have to give him any snacks at all to compensate. You can take away a toy with very little compensation because he has lots of toys. The slope of an indifference curve is called the marginal rate of substitution. And the marginal rate of substitution will be different as we move along the indifference curve. Up here, where the slope is steep, the marginal rate of substitution between snacks and toys is very large. If I take away one of your toys, I have to give you a lot of snacks to compensate. The marginal rate of substitution tells you how many snacks you would require in exchange for one toy. As we move down the curve, the marginal rate of substitution gets smaller and smaller and smaller. When we get way down here, where the curve is flat, the marginal rate of substitution is very small, which means if I take away one of your toys, then I don't have to give you very much snack at all to compensate you. That's because you've got a lot of toys. They're not as valuable to you in terms of snacks. So, a quick summary. The indifference curve slopes downward to represent the fact that both goods are desirable, and that you have to have more of one to compensate you for a loss of the other. Also, if you have more of both goods, you'll move up to a higher curve somewhere else, somewhere up here to the northeast. Finally, the slope of the indifference curve is called the marginal rate of substitution. And it's like a kind of internal price, a psychological price that you put on toys. If the marginal rate of substitution is big, then you want a lot of snacks to compensate you for the loss of a toy. Your price of toys in terms of snacks is high. But if you move down the curve and the marginal rate of substitution is small, then the price of toys for you in terms of snacks is small. That is, you're willing to give up a toy with very little compensation, with very little extra snack in return. This indifference curve, then, represents a set of combinations that Chris finds equally desirable. Well, let's look at another set of combinations that Chris finds equally desirable, but a set of combinations that provides him with more satisfaction than the combinations on this curve. Here's another table that represents a set of indifferent points for Chris. Chris would just as soon have 2 toys and 12 snacks as 4 toys and 6 snacks, 8 and 3, or 12 and 2. Now, all of these combinations are more desirable than the combinations on our original curve. How do you know that? You know that because right here we have a point that represents 12 toys and 1 snack. On this new list, we have the point 12 toys and 2 snacks. Since this involves more snacks and no fewer toys, that is, it's got more than the original bundle, it must be more satisfying because of our assumption more is better. Anytime you're moving to the northeast, directly to the north, directly to the east, or to the northeast in this diagram, you're moving to points that are strictly preferable, points and combinations that are strictly better. So let's go in and draw the picture that represents the combinations in this graph. Let's start with 2 toys and 12 snacks. That is, 2 toys and 12 snacks will take us up to this point. 4 toys and 6 snacks will take us to this point. And 8 toys, 2, 4, 6, 8 toys and 3 snacks will take us to this point. And finally, 12 toys and 2 snacks will take us to this point. Again, these are only a few of the combinations that provide Chris with this new higher level of satisfaction. If we connect these dots, we'll get a new indifference curve. Da, 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 da. Bam! All of these points are equally desirable. And all of these points are strictly more desirable than the points on the old indifference curve, since it's to the northeast, and more is better. Well, now that we've got a couple of indifference curves, we're going to need some labels to keep them straight. So let's call this original curve U0. U0 represents a number, and that number means the amount of satisfaction you get. We could call that utility. Utility is an economic term that means the amount of satisfaction that a consumer gets from consuming a bundle of goods. So U0 is the original level of utility or satisfaction, and we can label this new higher curve U1, which represents a higher level of satisfaction. Now notice I didn't put in numbers like 10 or 20 or 100 because, I mean, what would that mean? Numbers of utility. Measuring warm, fuzzy feelings in numbers. How do you do that? All I'm telling you is that however we measure satisfaction, the points on this curve represent a higher level of satisfaction than the points on this curve. One more thing to say about these indifference curves. Notice there are still points out there to connect with other bundles that are equally satisfying. I could spend all day drawing indifference curves, and these indifference curves would eventually fill up this graph. Indifference curves are everywhere dense. Every point on this graph has some other points that are equally satisfying, and I could spend all day drawing the lines connecting them. I would eventually have an indifference map, a complete representation of Chris's preferences. What can we say about this indifference map? We can say a couple of things. The first thing we can say is that the curves are everywhere dense. Everywhere you put your pencil in this graph, you are touching an indifference curve. The next thing we can say is that indifference curves can have all kinds of shapes. They don't have to be concentric circles. These indifference curves can be kind of weird blobby things as long as they're downward sloping and as long as the slope decreases as we move down the curve. One final thing, indifference curves can never, ever cross. Can you figure out why? I'll give you a hint. Remember, more is better. Let me show you. Suppose we had a situation up here where an indifference curve like this crossed over another indifference curve at a point like this. Now, how do we know that something like this can't happen? Well, we know from the following argument. Let's say we've got 3 points on this particular indifference curve, and we'll call them A, B, and C. Now let's take a couple of points that are on the other curve, and we'll call those points D and E. Now the thing that I want you to notice here is that point B is on both curves. That's what it means for the curve to cross. Well, according to this logic, D is northeast of A, that is, D has more stuff than A, so that must mean what? That's right, D is better than A. On the other hand, if you go down here, you'll see that since C is to the northeast of E, that must mean that this bundle, which has more stuff, is better. C is better than E. Well, if D is better than A, and C is better than E, we have a contradiction, because A is just as good as B, which is just as good as C. And if C is better than E, then A must, by transitivity, be better than E. However, we've already said that E is just as well liked as B, which is just as well liked as D. That's what it means for them to be on an indifference curve. Hold on. If A is better than E, and D is as good as E but better than A, then we've got a mess. We've got some kind of contradiction. How can A be better than E and worse than D, which is the same as E? Doesn't make any sense. It is illogical for these indifference curves to cross. You can't have more is better and have crossing indifference curves. So we'll put a big circle slash through this. This is not a possibility. Indifference curves never cross. Well, we've done a lot in this lecture. We've taken a set of preferences that Chris expressed, and we've represented them in a curve called an indifference curve, a collection of points that represent equally well-liked combinations of two goods. Then we saw that that indifference curve slopes downward, has a slope that represents a kind of psychological price called the marginal rate of substitution, And we saw that this indifference curve is part of a big indifference map that represents Chris's preferences for toys and snacks. Now, we're going to use this indifference curve along with the budget constraint to make some predictions about Chris's behavior, and eventually we'll be able to derive Chris's demand curve. What would you do if you had Chris's preferences and $12 worth of income? How would you allocate your limited income over all the possibilities available to you? Would you buy more toys, more snacks, a lot of one or the other, or a balanced combination? How do economists figure out what consumers are going to do given their preferences and given the constraints of income and price? We're going to put the indifference curves that represent preferences together with the budget constraint, which represents opportunities, to show you how economists think about consumer optimization. Consumer optimization is the behavior of households trying to maximize satisfaction subject to the constraints of income and prices. So let's take a look now at the graph that we've developed. First, we have this dark line, which you'll recall represents the budget constraint. That is, it represents all the combinations of toys and snacks that the consumer can buy given the limited income and the price of the two goods. My axes aren't labeled here, so it doesn't look like I have a meaningful graph. Someone's going to have to give me a label. Let's see. There's a snack, so we'll label the vertical axis with snacks. And here's a toy, so we'll label the horizontal axis with toys. Make sure that your axes are always labeled, otherwise your graphs are meaningless. Now, here we have the representation of the consumer's feasibility set. That is, the opportunities that the consumer has given income and prices. So if you spend all of your income on snacks at a price of $1 per snack and an income of $12, you can buy 12 snacks. If you spend all of your income on toys at a price of $3 per toy, you can buy 4 toys. And the slope of this budget constraint represents the relative price of toys and snacks, which is the price of toys at $3 a piece divided by the price of snacks at $1 a piece for a number of 3. 3 is the relative price of toys and snacks, and it's the slope of this green line. Well, I guess it's a blue line. It's the slope of this line. Notice one more thing. This line is downward sloping, which means that its number is negative. The true slope of this line is the negative of the relative prices, but let's ignore the negative sign for just a minute and focus on the intuition. How do you think about relative prices? How do you think about the slope of the budget constraint? This number 3 says this: if you will give up one toy, if you give up one toy, you're going to have enough extra income to buy 3 snacks. 3 is the relative price of toys measured in terms of snacks. Now, if this blue line represents your possibilities, what are you going to do? Well, economists imagine that consumers do one and only one thing. That is, they seek the combination of goods that maximizes satisfaction. Let's find that combination. Look at all of these red indifference curves that I've drawn in here for Chris. All of these red indifference curves represent combinations of goods and services that are equally desirable. Here's a low level of satisfaction. This level of satisfaction on this indifference curve to the northeast represents an improvement, and you can do even better by going way, way up here to the far northeast. The further to the northeast you go, the better off you are, because more is better in this model. Now I could go in and label these indifference curves. It looks like I've labeled this one U0. This represents our baseline level of satisfaction. And an improvement, we might call it U1, which means this curve represents more satisfaction. And I might label this curve underneath here, I might call it U-1, because it's worse. See, the numbers don't really matter as long as the numbers increase as satisfaction increases. Which point is going to be the most satisfying to Chris? The answer is simple. Chris is going to choose that point on his budget constraint that lies on the highest attainable indifference curve. Chris is going to find that point that gets him to the highest level of satisfaction, and that is the point that he will choose. In this picture, the highest indifference curve that Chris can reach is the one that I've labeled U0. And the combination of toys and snacks that maximizes Chris's satisfaction is going to be 2, 4, 6 snacks and 2 toys. With 6 snacks and 2 toys, how much money is Chris spending? Well, let's see. 6 times $1 apiece is $6 on snacks. And 2 toys times $3 apiece is $6 on toys. 6 and 6 makes a total of 12. And that, of course, is Chris's income, which is why this point is on the budget constraint. The total spending is equal to $12, the amount of money Chris has to spend. So, to find the point that gives Chris the most satisfaction, find the budget constraint, and then look for the indifference curve, the highest indifference curve that budget constraint touches. Now, there's something to notice about how to identify that highest attainable indifference curve. Notice that the budget constraint is tangent to that indifference curve. That is, the budget constraint touches it in one and only one place. Any other budget constraint, any other indifference curve, well, let me make sure I say this clearly. Any other indifference curve that touches this budget constraint will touch it in 2 places. Only at this highest attainable indifference curve do we have a single point of tangency. Let's look at some other possibilities. Suppose we look at this lower indifference curve. Notice this lower indifference curve touches Chris's budget constraint up here, and it touches it again down here. The thing to notice about these 2 points of intersection is that at both of these points, the indifference curve has a slope that's different from the slope of the budget constraint. That is, it's not a tangency, it's an intersection. It's a point where the budget constraint and the indifference curves have different slopes. The indifference curve cuts into and goes through the budget constraint. Here's a little bit of intuition to let you know why this can't be the best point for Chris. Think about this. At every point on the budget constraint, the slope is 3. That means Chris always has the opportunity to trade 1 toy for 3 snacks. Down here, at this particular point, the slope of the indifference curve is flatter. That is, the marginal rate of substitution is less than 3. That is, Chris would be willing to give up a toy for less than 3 snacks, maybe just for 2 snacks. Think about what that means. Chris is willing to give up a toy for only 2 snacks, but the market will give him 3 snacks. What's Chris going to do? Obviously, he's going to trade with the market. Obviously, he's going to give up his 1 toy and take his 3 snacks. 2 snacks would make him indifferent. 3 makes him better off. That's an improvement on his situation. So Chris starts moving up his budget constraint, trading toys for snacks until he finally gets to the point at which his desire to trade is equal to his ability to trade. That is, at this point, where the slope of the indifference curve, the marginal rate of substitution, is also 3, Chris is willing to trade 1 toy for 3 snacks, and that's exactly what the market will allow. At that point, Chris can no longer improve his situation by trading away his toys. He stops. He has reached an optimum. Look at this point up here. At this point, the marginal rate of substitution is very high, higher than 3. That is, that Chris would be willing to give up more than 3 snacks to get an extra toy. Aha, but the market will only charge him 3 snacks. He's willing to give up 4. So what's he going to do? He'll give up the 3 snacks and take an extra toy, and he's better off. He's better off because he was willing to give up 4 snacks, but he only had to give up 3. That is, he pockets an extra snack as he moves down the budget constraint. Chris makes himself better off. He continues to trade until finally the marginal rate of substitution is equal to the relative prices in the market. So there you have it. The condition for consumer optimum, the condition for maximizing satisfaction, is that the marginal rate of substitution is equal to the relative prices of the goods in the market. At that point, an indifference curve is tangent to the budget constraint. And that's the highest level of satisfaction that Chris can afford. Let's do a quick summary here. The budget constraint represents your opportunities, and its slope is the relative price in the market. The indifference curves represent your preference, and their slope is the rate at which you will trade off the goods, one for the other. The consumer gets the most satisfaction by finding the highest attainable indifference curve. That's going to occur at the point where the budget constraint is tangent to or touches the indifference curve at one place. The interesting thing about that point is that's the place where the relative prices are equal to the marginal rate of substitution, the slope of the indifference curve. That's the point at which the rate at which the consumer is willing to trade is equal to the rate at which the market will allow him to trade. Now, let's mess with that budget constraint and see how the optimum point moves around as prices change. This will get us a demand curve. We're back with our indifference curves and our budget constraint, and we're getting ready to derive the consumer's demand curve. Remember what we did last time. We showed that if you have a set of opportunities created by your income and prices, and a set of preferences, you're going to look for the most satisfaction you can get, given your constraint. That point of maximum satisfaction will be where your budget constraint touches the highest attainable indifference curve. Now, what's going to happen if your opportunities change? How will your behavior change if the constraint changes? In particular, how will Chris behave if we reduce the price of toys? Let's cut the price of toys in half, from $3 a piece to $1.50 each. What would Chris do in those circumstances? First, let's show in our graph the new budget constraint. With the price of $1.50 each for toys, the vertical intercept remains unchanged. We haven't done anything to the price of snacks or to Chris's income, so if he spends all of his income on snacks, he can still afford 12 snacks. However, if he spends all of his income on toys now, at a price of $1.50 per toy, he can afford to buy 8 toys instead of 4 like before. So here is Chris's new budget constraint. Our blue line here represents his opportunities with an income of $12 and a price of toys of $1.50 each. What's Chris going to do? As usual, he's going to look for the combination of toys and snacks that gives him the most satisfaction subject to this budget constraint. And that means looking for the highest attainable indifference curve. Well, it's clear that the highest attainable indifference curve in this picture is the one that's labeled U1. And the combination right here, 2, 4, 6 snacks and 2, 4 toys, that is 4 toys and 6 snacks, this particular combination represents Chris's optimal choice. Let's make sure that point's attainable. Of course, it's on the budget constraint, so we know that it is. 4 toys times $1.50 each gives us a total of $8, and 4 snacks at $1 apiece gives us a total of $4. 4 plus 8 is 12. Once again, Chris satisfies his budget constraint. How do I know that this particular combination is the best Chris can do? Because it represents a point of tangency between an indifference curve and the budget constraint. This is the point at which Chris's marginal rate of substitution, that is, his willingness to trade toys for snacks, is equal to the relative price of toys and snacks, that is, what the market will permit. You always find the optimal point where the indifference curve is tangent to the budget constraint. That's always the best that he can do. So, even though there are other indifference curves that are way up here to the northeast, Chris can't reach them because he doesn't have enough money. Even though there are other indifference curves that are below, they're irrelevant because they intersect the budget constraint. They're lower. Chris can get to a high level of satisfaction, the highest he can attain, by finding the point where the indifference curve touches the budget constraint at only one point. U1 is the highest level of satisfaction he can get. Notice what I did here. I changed the price of toys, and I looked at how Chris's optimal choice changed. He buys more toys than before. Before he was only buying 2. Now that the price of toys has fallen, Chris buys 4 toys. What I'm getting to is a demand curve. When the price changes, the quantity demanded responds, and that's what a demand curve is. In the next lecture, we will put the indifference curve budget constraint diagram that we have here before us, we'll put it on top of another axis and use this apparatus to derive a demand curve. What we're going to be seeing is the foundation for the demand curve, that is, where it comes from using this more basic theory. We've put indifference curves and budget constraints together to find the consumer's optimal choice under the constraint of the budget and prices. Last time, we showed how when the prices change, the consumer's optimal choice changes. Now we're ready to use the tool we've developed to show where the demand curve comes from. Where does a demand curve come from? It comes from consumers making optimal choices subject to their constraints. Look at the graph that we have before. Here I've reproduced it in a smaller form. The blue line represents the budget constraint. That is all the possible combinations of toys and snacks that a consumer can buy with limited income given the prices. The red line represents the highest attainable indifference curve, the most satisfaction that our consumer can get. And here's that optimal point. What I've done is taken the graph we derived and put another graph beneath it. And this graph is our familiar price quantity graph that we use for representing a demand curve. Notice on the horizontal axis, I've represented the quantity of toys, just like on the axis above it. Quantity of toys is measured on the same scale on both of these axes. So a quantity that comes down to this axis can be dropped on down into the graph below it. These two graphs are measuring the same thing horizontally. Vertically, this graph down below measures the price of toys. So originally, our original price of toys, which was $3 per toy, I call that P0, the original price. At a price of $3 per toy, then our consumer wanted to buy 2 toys a week, say. So here's a point on the demand curve. At a price of $3 per toy, the consumer chooses to buy 2 toys a week. Now, let's change the consumer's constraints by lowering the price of toys from $3 per toy down to $1.50 per toy. When we do that, we have to redraw the budget constraint in the diagram above. So here I go. I'm going to redraw that budget constraint, and I'm going to draw it very thick and beautiful so you can see it on the web. There you go. There's the new budget constraint. Now, with this new budget constraint, we're going to be looking for a new indifference curve. And that's the indifference curve that's going to be the highest one we can get to given the constraint of the blue line. And as we saw before, in the case of Chris's preferences for toys and snacks, that combination is going to be at a point like this. Here's the new indifference curve, call it U1, the highest attainable one. And here, right here at this point of tangency, is the combination that Chris would choose to purchase in that situation. So when the price of toys drops from $3 a toy down to this new lower price of $1.50 per toy, when the price of toys falls, the quantity of toys that Chris consumes increases from 2 toys a week to, in our case, 4 toys. So let me take those 4 toys a week, and with a dotted line, I'm going to go down below the axis, down into my downstairs diagram. And here's my new quantity, Q1, of 4 toys a week. So let's put a new price quantity dot right there at $1.50 per toy and 4 toys a week, and there you have it. Hey, once you've got 2 points, you can connect them, right? And that gives you a demand curve. So you can imagine if we kept doing this exercise, we'd get an endless combination of price and quantity points, and that becomes the demand curve for toys for Chris. So I've labeled this curve D, that's demand. And this curve does all those things that you've seen demand curves do before. What's the purpose of this lesson? The purpose is to show you where a demand curve comes from. And where does it come from? It comes from consumers who have preferences and who have constraints imposed by prices and income, doing the best they can with what they've got. As their circumstances change, that is, as prices change, the optimal choice will change. And the demand curve is a record of those optimal choices. As the price rises and falls, the optimal point will move around upstairs in this graph. And as it does, we record it downstairs in this graph, the demand curve. The demand curve shows you what the consumer will purchase, the quantity of toys Chris will buy as the price of toys changes, holding constant everything else, holding constant income, holding constant the price of snacks, holding constant Chris's tastes and preferences. That's where the demand curve comes from. And that's why we spent that time developing the indifference curve tool and putting it with the budget constraint and learning how to do consumer optimization.
Let's try and understand how consumers make choices. And we're going to look first at traditional consumer choice or utility theory. Utility is how happy somebody is or how much satisfaction somebody has. So as economists, we assume that people maximize their utility. They're going to maximize their utility subject to a constraint. Ideally, everybody would have everything they wanted of every good or service that they could possibly get. But that can't happen because we have limited resources. The resource that we're going to look at for consumers is our budget. We only have so much money we can spend. So the first tool we're going to look at is called the budget line. The budget line is a lot like the production possibilities curve. It represents every combination of 2 goods. Here we're looking at books and movies. The combination of these 2 goods that we can afford given our budget. If we spent all of our money on movies, we could go to 9 movies. If we spent all of our money on books, we could get 27 books. Or, depending on the prices of books and movies, we could do some combination in between. So this is our budget line. Like a production possibilities curve, we can afford to consume inside our budget line. So this shaded triangle is called our budget set. But you can't afford anything outside your budget line. Now, Now, what about the other side of our decision, our utility, or how happy something makes us? One of the important ideas about utility is diminishing marginal utility. The idea that as you consume more of a good or a service, your utility is going to rise, but it rises at a decreasing rate. So we can see the increase in utility from your 5th movie to your 6th movie is from 225 utils up to 261 utils, where utils are the units of utility. But the increase of your utility from 8 movies to 9 movies is only from 324 up to 351. So it does make you happier. It just doesn't make you as much happier as it did when you were only consuming 5 movies. So when we look at diminishing marginal utility, we can see that total utility is rising, but it rises at a decreasing rate. The important question is, what is marginal utility? And we see that marginal utility goes down as you consume more of a good or a service. So as more movies are consumed, the marginal utility, or the amount that your utility increases as you consume more of that product, goes down. We have diminishing marginal utility. Another important concept is looking at marginal utility per dollar. And if we're going to look at multiple goods and services, we need to compare how much marginal utility we're getting from each dollar that we're spending on a good or a service. So we look at our marginal utility for movies and divide it by the price of movies. Here, let's assume it's $3 per movie. Then our marginal utility per dollar is going to be this dark green line. This allows us to get to something called the equimarginal rule. The equimarginal rule is a way of describing how individuals make consumer choices. And the equimarginal rule says, pick the combination of 2 activities where the marginal benefit per dollar, here we're looking at the marginal utility, where the marginal benefit per dollar for the first activity equals the marginal benefit per dollar for the second activity. We can look at it as a formula here. Marginal utility for movies divided by the price of movies is equal to the marginal utility for books divided by the price of books. Now let's see why this makes sense. Let's look at its values. All right. If we're going to maximize utility, here are different points on our budget line. We could go 1 movie and 24 books, or 8 movies and 3 books, or 3 movies and 18 books. And what we want to look at is which combination is going to maximize utility. Let's look at an example. Suppose we started at this point with 4 movies and 15 books. And suppose those 4 movies got us 42, a marginal utility of movies of 42. Meaning if we went to 1 more movie, or that last movie got us 42 additional utils of utility. And when you have 15 books as part of your consumption, your marginal utility of your last book was 8 utils. Now those are hard to compare because we're not sure how much we had to spend on each one. So it's more useful to look at the marginal utility per dollar for each good. So again, if we're looking at this combination right here, for this combination right here where we're doing 4 movies and 15 books, let's see if this is as happy as we could be. Well, our marginal utility per dollar of movies is 14. So the last dollar that we spent on movies got us 14 utils. The last dollar that we spent on books got us 8 utils. The marginal utility per dollar for books was 8. So another way to think about that is if we spent 1 less dollar on books, we'd have 8 fewer utils of utility. If we took that dollar and spent it on movies, we'd get 14 more utils of utility. So we would give up 8 utils from books and get 14 utils from movies. That says we should do exactly that. We'll be better off. So we should not consume 4 movies and 15 books. We should consume another movie. Anytime the marginal utility per dollar is not equal between the 2 books, you can maximize your utility or increase your utility by changing your consumption bundle. So the equimarginal principle rule says, let's go to where they're equal. And that's going to be with this combination here, with 6 movies and 9 books. We can see that if we consume this bundle, the marginal utility per dollar from movies is 12. The marginal utility from books is also 12. So the blue circled bundle with 6 movies and 9 books is going to be the one that maximizes utility.